The title is capacitance. Okay, with this would be the last chapter for electric fields. Once we are done with this, we'll be moving to magnetism. Okay, or capacitance is simply the application of everything we have studied till now. Last chapter we talked about dielectrics. So we talked about certain properties of dielectrics. All those properties of dielectrics will become useful in this chapter, capacitance. So let me start off with asking you to recall something. You all know that a source of electric field is charge. A charge at rest will give rise to an electric field. You all know that. Similarly, you all know that if you have a positive sheet of charge and a negative, equal and opposite negative sheet of charge, if this is sigma plus and this is sigma minus, then you have seen that between these two plates, there will be a uniform field, and the field is given by the expression E equal to sigma by epsilon naught. I hope you remember this. Okay, and another thing that I want you to remember is the relationship between electric field and potential difference. If I take 2 points in space like this, and if I talk about their potential difference as VA and VB, then I can say that there is an electric field between these two. There is an electric field existing between these two, okay? And that electric field is going to be given by the equation dou V by dou, let me say, dou V by dou X, if I call this as my x-axis, dou V by dou X with a minus sign. Okay, and here when I'm talking of dou V by dou X, I'm talking of minus of VB minus VA divided by the distance. If X is the distance, then the distance is going to be X. Dx is simply going to be X. So this is the relationship between electric field and potential difference. And you can see that the direction of the potential difference, the direction of the field is decided by which of these is a higher potential. Okay. So this is what I wanted you to remember. Or in other words, you can simply write this as E is equal to minus dou V by dou R if I'm talking of 3 dimensions. And then another thing that I want you to remember is work done by the electrostatic force is going to be equal to change in kinetic energy. And it is change in kinetic energy because it is a conservative, it is change in kinetic energy. And the next thing is work done can also be written as negative of change in potential energy because electric field is a conservative field. And then the relationship between change in potential energy and potential is delta U is equal to Q naught into delta V. Or in other words, if I'm taking 2 points like this, A and B, and if there is a potential difference delta V between them, to take a charge Q naught from here to here, if I have to take a charge Q naught from A to point B, then the work done is going to be equal to, work done by the electrostatic force is going to be negative of the change in potential energy. Or I will say negative of the work done by the electrostatic force is equal to delta U, which is Q naught into delta V. So these are the 3 things that you should know before we get into this particular chapter. Next, what are all the things that we'll see in the chapters? The first thing is, what is a capacitor? Then what are the factors that decide the capacitance value? Then different geometries of capacitors we'll take and arrive at the expressions. Then how do you combine capacitors to get the capacitor value that you desire? Then what is the use of a capacitor? You're going to see that capacitors can be used to store energy. Okay, next thing is, how do you change the energy storing capacity of a capacitor? We'll notice that we can actually put dielectrics into the capacitor, then we can change the energy stored. And lastly, applications of capacitors. So these are the various things that we'll be quickly going through in this particular chapter. So let's do it one after the other. So the first question is, what is a capacitor? What is a capacitor? So the answer is there for you. Capacitor is simply a circuit element. That's the first thing you should remember. A capacitor doesn't act alone. A capacitor is a part of a circuit. So it's called a capacitor is a circuit element. Circuit element is a word. Capacitor is a circuit element, or you can say it's a device which can be charged. So you can charge it and you can store energy in it. Have you come across capacitors in real life? Anyone? Have you come across capacitors in real life? Anyone?
In electrical appliances like fans.
Like fan. Okay. Somewhere else where you hear the word charging and all that. In a camera, the flash of a camera, there is a capacitor. Actually, every time you're going to use the flash, you have to charge it. Okay, there is a battery inside and you're going to charge it. And what happens in a capacitor is it is able to take the charge, store energy, and give it out in a burst. So in a flash, what happens is you need a large burst of energy in a very short interval of time. Okay, so a capacitor you typically find there also. And what do you see in a capacitor? Everywhere there is a capacitor, you are going to see two conductors, which we will call as plates. Okay, and they will be isolated from each other, meaning they're not going to physically be touching each other. They will be isolated from each other. And when you charge them, they will carry equal and opposite charges. Okay, once more I repeat, any capacitor should consist of two conductors separated from each other, isolated from each other, and they can be charged. And when you charge them, they will carry equal and opposite charges. And these two conductors are going to be called plates. Like for example, if I'm just going to take a knife, a metallic knife, and if I'm going to take, let us say, a glass in the kitchen, if I put them like this, they also form the plates of a capacitor. They need not have any specific shape. Okay, these also become a capacitor. They can act like a capacitor. It's possible to make them as plates of the capacitor and charge them. Okay, now what is this charging? What is the process of charging, let us see? And for charging, you need a source of EMF. For charging, you need a source of EMF. And mostly that source is going to be a battery. I hope you remember from last two chapters, that a current flows from a dash potential to a dash potential. A current flows from a point of dash potential to a dash potential. When I say dash, I want you to fill it up with low, high. What is the order in which you will fill it up? Anyone?
Higher.
Higher to a lower potential. I normally ask my students to remember it this way. Water flows from a higher potential, higher gravitational potential to a lower gravitational potential. Yes or no? Water always flows down from a point where the gravitational potential energy is higher to a point where the gravitational energy is lower. Down a hill. H stands for H stands for high, and L stands for low. So water always flows from a higher to a lower potential. Just take the same idea and then talk in terms of current. Current also flows from a higher potential to a point at the lower potential. But please remember, this potential difference that you have to create in a circuit. Let's take this part of the circuit. Okay, so this can happen only. How do you actually create this potential difference between these two ends? You can create this potential energy by putting a battery, a source of EMF you have to place, so that the positive terminal is here and the negative terminal is here. So this will be a higher potential and this end will be at a lower potential. So the flow of current will be like this. Flow of current will be like this. And here is a switch, you can close it. Okay, so the switch is there. If you close it, then the flow of current is in this direction. What will be the direction of the flow of electrons? What will be the direction of the flow of electrons? Anyone?
Opposite to the direction of current.
The flow of electrons will be in the opposite direction. Electrons will be flowing in the opposite direction. Okay, and you're going to see that. So what is essentially happening is the electron is going from a point which is at a lower potential through the circuit to a point which is at a higher potential. Or in other words, so here what you're going to see here is electrons are going to move from one plate and get deposited on the other plate. Electrons will get moved from one plate, okay, and get deposited on the other plate. So initially what will happen is both the plates will be neutral, no charge. But once you put the battery, the job of the battery is to do this job. So electrons get pulled out. And you can see that this complete circuit is there only here. The full circuit is here. Actually, here there is a gap. and you know that within a gap, no current flows. Okay, so you have to understand, though we say the current is flowing like this, you have to talk in terms of the electron flow. The electrons are getting pulled out the from this plate and then getting deposited on the other plate. So slowly, what will happen is you will find that this plate slowly starts becoming negative and this plate starts slowly becoming positive. And you will find that this charge is going to be a function of time. Initially, the charge is zero, then slowly the charge starts building up, and finally, when the charging is over, okay, when the charging is over, you won't find any more current in the circuit. Let me ask you a question. When will the current in the circuit be a maximum? When will it be zero? Just try to answer. This current in this circuit will be maximum at some time and it will be zero at some time. When will it be a maximum? When is it easy for you to pluck out electrons from a neutral body, from a body? I've given you the answer. To pull out the first electron is easy.
When resistance is zero, ma'am.
No, I didn't mean that. Energy-wise, how easy is it to pluck out the first electron when compared to the second electron? I have a neutral body. To pull out one electron is easy. Okay? But then to pull out the second electron becomes more difficult. It becomes more and more difficult to keep taking out more and more electrons, because what is going to happen is this body is going to become positive. Every time I'm going to pull out an electron, this is going to become more and more positive. So it doesn't allow me to pull out more electrons. Okay, so what happens is initially at a time t equal to 0, the current will be a maximum. It is easy at that time because both are neutral. But then at t equal to, let me call it as infinity, that is when the charging is completed. At that time, t is not equal to infinity. Actually, if you study, you will find that there is something called the tau is equal to RC. That is the time period. So after that, what will happen is you will find that the current will tend to 0. The current will become 0. This is after charging. T is equal to T max, which is when the charging is completed. Okay, and initially when the two plates are neutral, then what is the potential of a neutral body? What is the potential of a neutral body? What is the expression for potential for a charge? Potential is equal to 1 by 4 pi epsilon naught.
Q by R.
Q by R. Q by R. So if Q is going to be 0, that means the potential is going to be 0. So initially, okay, at a time t equal to 0, VA will be equal to VB will be equal to 0. But then the minute you connect your battery, then once you start plucking out the electrons, then slowly you can see that the velocity, the potential is proportional to the charge. Therefore, you're seeing that as the charging keeps taking place, this A and B are going to slowly start having a different potential. One is going to be positive, one is going to be negative, or finally after the charging, there is a maximum potential difference between the two plates. Okay, so let's call this potential difference as delta V. You find that the potential difference between the two plates will be directly proportional to the charging that you have done and the way you have deposited charge by pulling out charge from one plate to the other. Is this point clear? Are you able to understand that initially the two plates are neutral and there is no potential difference? Is that clear?
Yes,
Yes, ma'am.
Right. Slowly, are you able to see that one becomes positive, one becomes negative, but they carry small charges. So there is a potential difference, but that potential difference is small. Then slowly, as the charging increases, you know that potential is directly proportional to the charges contained by each of the body. Therefore, what happens is one becomes a large positive, one becomes a large negative. So the potential difference becomes a maximum. Or simply you can conclude saying that the potential difference is proportional to the charges on the plates. And when we say charge here, we are talking about the magnitude of the charge. We are talking of modulus charge. We are not talking about positive, negative, or anything like that. the magnitude of charge contained by any one plate is Q. I hope this point is clear. Okay. Then finally, you finish your charging. When do you think the charging gets over? Is there any upper limit to the charge? Ideally, if your battery is, let us say, able to give 120, if your battery is able to give a potential, the battery's voltage it's able to give is, let us say, 20 volts. 20 volts. Then what happens is, this capacitor also ideally should be able to reach that 20 volts potential difference. After that, you won't find any more current flowing. This is ideal. But most often what happens is the capacitor will stop charging even before that 20 volts. 20 is just a hypothetical number that I'm telling. So that sets the upper boundary. Okay. After that, what will happen when both of them, when the battery's potential difference and this fellow's potential difference becomes the same, then what happens is this is positive, this is negative. Similarly, here this plate will become positive, this plate will become negative. So there is no potential difference between the plate, the terminal, the battery terminal, and this plate. So there is no potential difference, so there will be no flow of current or charges. Let me once again repeat. After the charging is completed, the potential difference between the battery will be the same as the potential difference between the plates. So what happens is, if I take one of the terminals of the battery and one of the plates here which are connected, you will find that they are at the same potential. So this entire conductor which is connecting them is at the same potential. So there is no further flow of charges. Same with the other plate and the other terminal of the battery. So I hope I made you understand why the current becomes zero. Is this clear?
Yes, ma'am.
Right. So now let me just go ahead. You do one thing. Just look at this once. I need to drink some water. Let me drink some water and come. Please give me a 1 minute break. Okay, thank you. So now let's move to the next page. Okay, so now the charging has happened. So now instead of showing two plates, we are showing them as two bodies. The two plates can be simply treated like two bodies, one carrying positive charge, the other carrying negative charge. And then I told you the charge each of them carries is directly proportional to the potential difference. And when we are saying potential difference also we are taking as larger minus smaller. Larger minus smaller. That's our definition of delta V. Delta V is not negative. Delta V by definition is not negative in this situation. When we talk of potential difference, we are talking about modulus of the potential difference. Similarly, when we say charge also, we are neither talking about a positive charge or a negative charge. We are talking about the charge on one plate, the magnitude of the charge. Okay, that's the reason why we write delta V as V plus minus V minus, because the positive plate is always at a higher potential. Now look at this. Q directly proportional to delta V. So we can write this as an equation with a proportionality constant. Or you write Q is equal to C into delta V, where C is the proportionality constant. Okay, it's a proportionality constant. And this C is called the capacitance value of this configuration of two conductors which have been charged. C is called C is a proportionality constant here, and C is called the capacitance value of this configuration of two conductors. And from here you get capacitance is equal to Q divided by delta V. Okay, and if you look at the unit, you can see Q is charge, coulomb, and the potential difference is volts. So you can say it is it is coulomb per volt. You can say it is coulomb per volt, or another name for coulomb per volt is farad. Coulomb per volt is also called farad. Okay, and normally you are not going to find capacitors in real life which will have 1 farad value. It will be normally microfarad, nanofarad, picofarad, mostly picofarad also. Pico is 10 to the power of minus. Anyone? Pico is 10 to the power of minus.
12.
Yeah. And micro is 10 to the power of minus 6. Nano is 10 to the power of minus 9. Okay. So you will find that capacitance value will be very small. That's not difficult for you to understand. Look at Q. You've seen in one of the chapters that you can't disturb the charge equilibrium of a body greatly. You cannot pull out a lot of electrons. You've seen in one of the chapters. So that explains why the capacitor value cannot be very large. Now there is a catch. There's something I want to ask you. I have a capacitor. I have a capacitor. This is my capacitor. Okay. Now, at a time t equal to 0, they don't carry any charge. They don't carry any charge. What is the value of capacitance? Listen to my question carefully. At a time t equal to 0, when it is not charged, what is the value of the capacitance?
0.
No. No. Nice. But I asked that question. No. It is C. C is a constant. C is a constant. It is not 0. In a few minutes, you're going to see that the capacitance of a capacitor just depends on its geometry only. It doesn't depend on whether it is charged. It doesn't depend on whether there is a potential difference. So this is an important point that you should remember always. Okay, capacitance value does not depend on how much charge it is carrying. It does not depend on what is the potential difference. It just depends on the geometry only. But the relationship between these two variables and that constant is given by this equation. That's all. I hope I made myself clear. Yes or no? C is a constant that depends on geometry only, not on Q and delta V. Even if Q is 0, the capacitance value is a constant. Now, next I have asked you a question. Any limit on the amount of charge Q? That already we have answered. Charge transfer will be taking place till the potential difference between the battery becomes same as the potential difference between the plates. So that's the limit on the charge. Okay, next. Now look at these two, this plus Q and minus Q. Let's go back to this figure 30.01. You can see that there will be always field lines starting from the positive ending on the negative, right? Now, this field line representation, does it remind you of some field line representation you have seen previously? Does this magnetism we have not even studied. One of the chapters, you have studied a field line representation which looks similar to this. Anyone? Nobody is studying anything. A plus Q or minus Q separated by a distance. What is that?
Electric field line.
Electric field line. These are also electric field lines. Electric field line of what charge? What charge configuration? What is that entity called? A plus Q or minus Q separated by a distance. What is it? A dipole. A dipole. Only thing is plus Q and minus Q, there are point charges. But in this case, plus Q and minus Q are not point charges. They are actually charges on plates, extended charges. But then you will see that they look similar to a dipole, and you can see how the field lines look. The field lines also look similar to a dipole. Please learn to connect like this and see. Only when you connect like this, no, you will be able to understand why this drawing came like this. Why does this drawing look like this? You will be able to understand only then. Okay, and then now you just, for a minute, think about these two bodies being just sheets. These two bodies just being sheets, one positive and the other negative. Okay, then what happens is you will find that a similar charge configuration will be there. Let me show the charge lines with red line. Okay, similar charge configuration will be there. You may find like this only, you may find like this only, you may find this, you may find this. It's very, very similar to what you're seeing in the above picture. Okay, the only difference is going to be that between these two plates in this region, okay, between the two plates, you're going to see a number of parallel lines. What are parallel lines? Parallel field lines imply
Uniform electric.
uniform electric field. Uniform electric field. So if these two plates of a capacitor happen to be parallel conductors, then and if they are charged, then you're going to have uniform field between the two plates. Okay. For other configurations, you won't have a uniform field. So now let's just set up some equation. Okay, so what is that equation? Let's see. The potential difference between the two plates, which is V plus minus V minus, can be written as minus integral minus 2 plus E dot dl. From where is this coming? Anyone? Where is this coming from? Chapter 28, or what I have asked you to recall. It comes from there. E is equal to minus dV by dl. It comes from there. Okay. Now what you do is you just change the limits. You just interchange the limits of integration. Then this minus sign will go. It becomes integral plus 2 minus E dot dl. Plus 2 minus E dot dl. Which means if I'm going to have two plates, one positive and then one negative, then I can talk about an electric field line. It may be a straight line. It may not be a straight line. But whatever it is, there is going to be an electric field line which you can travel along some path. Okay, if you travel along some path, then for this entire path starting from positive to the negative plate, if I integrate E dot dl, where dl is a line element here, then that will be simply equal to the change in potential between these two bodies. This is the physical interpretation of this particular equation. And this equation we will be using again and again in this particular chapter. I hope all this is clear to you till now.
Yes, sir.
Okay. So now let's just work out a problem and see how much you've understood it. A storage capacitor, I told you it's used to store energy. So a storage capacitor on a RAM chip. I'm sure you all heard of RAM chip inside your computers. Okay, it has got a capacitance and the value of the capacitance is 0.055 picofarad. Pico is 10 to the power of minus
50.
Anyone else with some other answer?
Minus 12.
Minus 12, minus 15. Okay, that's the reason why I keep asking you to repeat it. It's not that I don't know. I ask you to tell this again and again. Many times you must have noticed. Okay, it is 0.05 centimeter or 0.05 into 10 to the power of minus 2 meter. We keep telling that again and again so that you will remember. So it's 0.055 into 10 to the power of minus 12 farad. Then it is charged to a potential difference delta V of 5.3 volts. Now what is asked is, how many excess electrons are there on the negative plate? How many excess electrons are there on the negative plate? So first of all, let's find out what is Q. What is plus Q and minus Q? Let us find out. How do I do that? Q is equal to C into delta V. So let's just put it there. 0.055 into 10 to the power of minus 12 into 5.3. Okay. So that gives me in coulombs the charge on each of the plate. But what is asked is, how many electrons are there? So how do I get the number of electrons? How do I get the number of electrons? Let n be the number of electrons. Yeah. Total charge is Q. What is the charge of one electron? It is E. Okay, then I will be able to get N into E is Q. Okay, so that's all I'm going to do here. So I can just use 0.055 into 10 to the power of minus 12 into 5.3. That gives me Q in Coulomb divided by charge of one electron, 1.6 into 10 to the power of minus 19. You must notice that I'm not putting a minus sign there. I'm not putting a minus sign simply because we are talking of number of electrons. So I don't have to put a minus sign there. Okay, so let's see the answer. Let's see the answer here. Yeah, so I have the answer here. It says 1.8 into 10 to the power of 6 electrons. Charge on each plate will be 1.8 into 10 to the power of 6 electrons. What is the number percent per unit volume of a metal? First class we have seen 10 to the power of 28, 10 to the power of 28. And what is this? Just 10 to the power of 6. That's a small drop, a small drop. That's why I told you, you won't have large capacitances because you can't disturb the charge neutrality of a body much. Okay, so 10 to the power of 6 electrons. It's very small when compared to what it will have. So this is a very small number, a speck of household dust. A speck of household dust, like what you just open the window, you will find this dust particle in the sun. Okay, so a speck of household dust. It's so small, it will not settle at all. It will be floating in the air. That will contain 10 to the power of 17 electrons. The author is writing it just for you to have a feel. A speck of dust which you open the window and when the sunlight comes in, you will see those dust particles floating. They are so small, they will never settle anywhere. Even such a speck will have around 10 to the power of 17 electrons. But look at the number of electrons, excess electrons on the plates, it is just 10 to the power of 6. So you can't disturb the charge neutrality of a body much. That's what this problem is essentially trying to tell you. Okay, now we will get into the geometry of various capacitors. I said the plates, they are called plates, but then they can have any shape, I told you. Okay, now let us get into the geometry. We will start with parallel plate capacitor. So as the name itself suggests, you're going to have two plates which are parallel to each other. They're going to be plain plates. Remember, both are conductors. And these two conductors, they are not touching each other, but after charging, you see where the charges are. Normally, if I just have a piece of metal and if I charge it in electrostatic equilibrium, where will all the charge be? If I just have one single metal piece, I charge it and at electrostatic equilibrium, where should all the charges be? If I say this is a piece of metal, I've charged it, okay? It is having some extra charge, one single piece of metal, and then I allow it to reach electrostatic equilibrium. Where will all the excess charges sit? Anyone? My God, it's impossible. Yeah, nobody is studying anything. All the charges will go and sit on the two surfaces. All the charges will go and sit on the surface. An electric field inside will be zero. That is electrostatics. But now you look at this. Here, what is happening is there are two bodies. There are two bodies. They are isolated from each other, all right, but still interacting with each other. So you will find that the excess positive charges are going and sitting on the inner surface. Similarly, the excess negative charges are going and sitting at the inner surface because of the attraction. This you should remember whenever you are dealing with capacitors and drawing diagrams. And you can see that the field lines are going to be uniform from the positive plate to the negative plate. Okay. And what is the value of that field? The value of the field is going to be sigma by epsilon naught. What is sigma? Sigma is the surface charge density. Sigma is charge on a plate divided by the area of the plate. So that's the reason why you can say that the electric field is going to be Q by A epsilon naught. and the direction of the field is from positive to negative. And we have seen how this formula is coming. It is coming from the addition of the field due to the positive plate and the field due to the negative plate. Now what we are going to do is, we are just going to take this equation that we got in the previous page. Potential difference is integral of E dot dl, where the integration is from plus to minus. We are just going to take this equation, and into this equation you substitute for E. You substitute for E. You can see that E and dl are parallel. What is dl? dl is just going to be a length element here, dl. And what is E? E is parallel to it. So E dot dl will be equal to E dl. Okay. And what we will do here is, I need not put this, I'll simply say it is E dl. And let's substitute for E. E is Q by A epsilon naught. Okay. And integral dl from plus to minus, if you do, it is simply going to be the distance between, the inner distance between these two plates. If I call this distance as d, then delta V will be equal to QD by A epsilon naught. Delta V will be QD by epsilon naught into A. But a few minutes back, we have seen that C is equal to Q by potential difference. Q by potential difference. So what we will now do is, we will substitute for this delta V. So delta V, when you substitute here, will become QD. Then A epsilon naught will go up. Q and Q will cancel. So you will get epsilon naught A by D. Have you come across this expression? C is equal to epsilon naught A by D. Looks like you've not heard anything. Okay. So this is the formula for the capacitance of a parallel plate capacitor. What is A? Area of the plate. Area of the plate, not cross section. A is the area of the plate. What is D? D is the gap between the plates. Okay. And epsilon naught is the electrical constant of the medium inside. The medium inside is simply vacuum or air. So now this is a very, very important result. Look at this. Capacitance of a capacitor depends on its geometry, not on the charge of the plates and the potential difference between the plates. This is what I told you a few minutes back. Even if the capacitor is completely uncharged, even if Q is equal to 0, then also capacitance value will remain. It is a constant. It depends on the geometry. These are the questions that we can ask in your MCQs. Okay, now let's go to another geometry. The next geometry that we are going to see is going to be a spherical capacitor. As the name suggests, there will be two spheres. The inner one is going to be, it doesn't matter whether it is a solid sphere or a hollow sphere, because anyway the electric field inside is going to be 0 when I charge it. So it doesn't matter. So inside there is one sphere and outside there is a shell concentric to the inner sphere. So because of the shape, it is called a spherical capacitor. Now we have to, just as we talked about area A and distance D there, here we will talk about the parameters. We will say A is the inner radius of the inner plate. Here also we'll call them plate. Plate is a general terminology. So the inner plate has got a radius A, and B, look at B. B is the inner radius of the outer plate. B is the inner radius of the outer plate. Or we can call them electrodes also. Once again, I'll tell you, A is this distance from the center to here. What is B? B is from the center to the inner surface. And A to B, what do you have between A to B? A to B, you have nothing. A to B is simply free space. A to B is simply free space. Now let us say you have charged it. When you charge it, what will happen? Let the inner plate be positive. Outer plate is negative. Like in the previous case, you can see that all the electrons, excess electrons will come and sit on the inner surface. And all the positive charges are going and sitting at the outer surface of the inner sphere. Okay. So what will be the field inside the body of the inner? Inside, the field will be 0. Okay. What will be the field here? Anyone? Use Gauss law and tell me what will be the field here. Here also it will be 0. In both the pink areas, the field will be 0. Okay. What about the field here? Here. Within the gap, will there be field? There will be field. The field will not be equal to 0. Guys, I'm not talking some new thing here. If I take a Gaussian surface like this and try to apply Gauss law, I'll find that everywhere inside the field will be 0. Similarly, if I take a Gaussian surface here and see the net field and charge enclosed is plus Q minus Q 0. Therefore, the field will be 0. So in all the pink portion, electric field will be 0. But in this white portion, in the gap between the plates, electric field is not 0. Okay? And what is the electric field? The electric field in this region will be given by E is equal to Q by or 1 by 4 pi epsilon naught into Q by R square, which is simply the expression that you use for a point charge. This behaves like a point charge. So the electric field inside this between the gap is given by 1 by 4 pi epsilon naught Q by R square. For the region A less than R less than B. A less than R less than B. That is between these two plates. Okay. Now once more, we are going to take this expression for the potential difference. Okay. There we wrote plus 2 minus. There we wrote plus 2 minus in the integral. Here we will write A to B. R equal to A. It is R equal to A to R equal to B. R equal to A is at the higher potential plus. R equal to B is at lower potential minus. Okay. And once more, you're finding that what is dr? Dr is going to be this. This is going to be dr. Okay. Or you find that the electric field at any point is parallel to dr. Therefore, integral E dot dr is going to be integral E dr. Okay. Now what you do is substitute for E. Where do I get that? I get that from here. Substitute for E. I find that Q by 4 pi epsilon naught is a constant. I can take it out and do the integration of integral dr by r square within the limits A to B. So when I do this, I get Q by 4 pi epsilon naught 1 by B minus 1 by A. 1 by B minus 1 by A. Upper limit minus lower limit. So 1 by B minus 1 by A. Next, I can just take the LCM. I can actually take the LCM and, wait. What did I do here? Have I made a mistake? Anyone? Have I made a mistake there? In typing, yes, I think I made a mistake. So what happens here is, what should be there on in the denominator and numerator? Anyone? Here I should have AB, and here I should have B minus A. Numerator I should have B minus A. Am I right? Yes or no?
Yes.
You people will kill the confidence of a teacher by not answering anything. Okay, so I got the expression for my potential difference. Once I get the potential difference, then again I have to go to my famous definition of my capacitor, which is Q by delta V. So just substitute for delta V here. So that becomes Q by 4 pi epsilon naught B minus A by BA. Okay, so that simply becomes 4 pi epsilon naught. Okay, so I need to just look at this once. 4 pi epsilon naught B minus A by AB. Just we have to just check this. 1 by R. So this is going to be AB by B minus A. Let me just correct this. AB divided by B minus A. Okay, so this is the expression for the capacitance value of a spherical capacitor. Okay, once more. What is it you're finding? The capacitance value depends on the capacitance value of the spherical capacitor depends on the geometry. What are the geometric parameters here? A and B. Of course, it depends on epsilon naught, which is the medium. Next thing is it depends on the geometric factors A and B. Okay, now try this problem. Try this. The plates of a parallel plate capacitor are separated by a distance 1 mm. What should be the plate area be if the capacitance value has to be 1 farad? I told you 1 farad normally you don't find. So what is the formula, guys? C is equal to epsilon naught A by D. So I want A. So A is going to be CD by epsilon naught. So let's just put it here. C is going to be 1. D is going to be 1 mm, which is 1 into 10 to the power of minus 3 meters, divided by 8.85 into 10 to the power of minus 12. Okay. 1.1 into 10 to the power of 8 meter square. 1.1 into 10 to the power of 8 meters square. How big you think it's going to be? 10 to the power of 8 meters square. What is 10 to the power of 4 into 10 to the power of 4? What is 10 to the power of 4 into 10 to the power of 4?
10 to the power 8.
10 to the power of 8. So that means here we are talking about a square whose one side is 10 to the power of 4 meters. And what is 10 to the power of 4 meters in terms of kilometers? 10 to the power of 4 meters is how many kilometers?
kilometers.
10 kilometers. 10 kilometers. With two plates with 1 mm gap between, and the size of each plate is 10 kilometers by 10 kilometer. Sorry, it is not possible. Sorry, it's not possible. Okay, you can't have a parallel plate capacitor with 1 farad. I told you, you won't have 1 farad. It will be micro, nano, pico. Now you understand why it is so? This is the reason. Okay, and another thing is, you must also notice what is the D value given. Look at D, it is millimeter. So another lesson from this chapter is, from this problem is that in a parallel plate capacitor, the plate area will be bigger, much bigger than the gap between the plates. Only then you will have uniform field. Okay, and then, okay, now if that is the case, this 10 kilometer cannot be there, we are saying. Then why at all this problem is there? That we have to find out. So the reason why this problem has been given is to tell you that you can't have such a large farad value, capacitance value for parallel plate capacitor. Next thing, it is also trying to tell you that the gap between the plates has to be of the order of millimeter. And finally, it is telling something else. It says the farad is a very large unit. Modern technology, however, has permitted the construction of 1 farad capacitors of very modest size. But then the technology is different. Those capacitors are called supercaps, and they are used in computers. Okay, and mostly they are used for memory, storing memory, and they are not your normal parallel plate capacitor. So a normal parallel plate capacitor cannot have that kind of a value. If you look at a normal capacitor in a lab, it will look so small it will be. So it cannot have 1 farad. So 1 farad is a super cap. The technology itself is different. Okay, now here is another problem. Continue to write wrong things, speed. So 4 pi epsilon naught AB by Yeah. AB divided by B minus A. Minus A. Okay. So here is a question. What is the capacitance value of Earth if you view Earth as a conductor? You know Earth is a conductor. There's no doubt on that. If you view Earth as a conductor and talk about a mean radius, you know that the Earth is not a sphere. The radius is different at the equator, different towards the poles. But then if you assume a mean radius of 6,370 kilometers, what will be the capacitance value? Can someone do this and explain this? So what is a spherical capacitor? It should have inner radius A and the outer one's radius should be B. But we are talking of Earth. Earth is simply, let me use green for Earth. So I'm talking of Earth. Earth is simply a single sphere of radius R. So where is the second plate? Where is the second plate? Anyone? Capacitor should have two plates. No, where is the second plate? Yesterday I was talking to a friend of mine working in SRM. She said, I am not going to break my head. I will go. I tell them, you listen if you want to. Otherwise, I'm just teaching. I teach, I come out. So maybe I should also do that now. No frustration. Okay, where is the second plate? I'll answer. The second plate is at infinity. Or B tends to infinity. This is what you have to remember. So now let us write the formula. C is equal to 4 pi epsilon naught AB divided by, okay, let's take out B, then 1 minus A by B. You'll get. If I take B common out, then it will be 1 minus A by B. Now put limit B tends to infinity. When B tends to infinity, what will happen is this B and B will cancel out. A by B tends to 0. This A by B tends to 0 because B tends to infinity. So denominator will have only 1, or you will get C is equal to 4 pi epsilon naught A. And what is A? A is only R. Okay, so you get 4 pi epsilon naught R. So the formula for the capacitance is going to be C is equal to 4 pi epsilon naught R if I'm talking about an isolated capacitor with only one plate. So now let's just put the values. So 4 pi into 8.85 into 10 to the power of minus 12 into the radius. Radius is 6370 kg. 6370 into 10 to the power of 3. Okay, you put it, then you will find that the value is going to be 710 microfarad. 710 microfarad for Earth itself. Look at the value of the capacitance. It's just microfarad. Okay. So all the more, you must be convinced that you can't naturally, with normal technology, have capacity. Is there anyone who has a doubt in these steps that I wrote? Okay, now let's go to the third configuration, third geometry. The third geometry is going to be cylindrical capacitor. So cylindrical capacitor, if you look from outside, is going to look like this. Okay, so this is going to be a metal. Maybe some thickness is there. We are not bothered about the thickness. We only bother about the inner dia. Radius, it's B. And then inside that concentric is going to be another tube or a rod, okay, of radius A. Radius A. And you know that within the body of, from Gauss law, within the body of both these metals, there is going to be field 0, just as in the case of sphere. The positive charge will be sitting on the outer surface of the inner electrode, and the negative charge will be sitting on the inner surface of the outer plate. And between these two, and let this dimensions be A and B. Now between these two, there will be a field. I'll call this direction as dr. Okay, and there is an equation for E. This comes from Gauss law. The equation for electric field is for this kind of a body, it is lambda divided by 2 pi epsilon naught r, which is charge on the inner plate divided by 2 pi epsilon naught r L, if L is a length. Okay, so I'm just going to use this into this formula. Okay, and then again I find E is parallel to dr. Okay, therefore integral E dot dr becomes E dr. Then I substitute for E, pull out all the constants. So I will just be left with dr by r, integral dr by r with the limits a to b. So integral dr by r is log r, substitute the limits, log r, substitute the limits a, b. So that becomes log of b minus log of a. Log of b minus log of a can be written as log of b by a. So that's all you're going to do here. So log b by a into q 2 pi L epsilon naught, where L is the length. L is the length. Okay. So you get delta V. Delta V is the potential difference between the positive and the negative. Now again, go to the equation C is equal to Q by delta V. Substitute for delta V, you get the expression for the capacitance. Once again, you find that the capacitance value is depending on only the geometry. What are the geometrical parameters here? A, B, L. Of course, epsilon naught is a medium. Okay. Now, many times you will not be talking about capacitance of a cylindrical capacitor. Where do you see cylindrical capacitors? I'll tell you. Even your coaxial cable which comes to your TV, okay, they are all like cylindrical capacitors. You will normally talk about capacitance per meter length. You'll talk about capacitance per meter length. That means C by L. So C by L is therefore going to be 2 pi epsilon naught by natural log P by A. Now let's just work out this problem. The space between the conductors of a coaxial cable, just now I told you coaxial cable. Have you seen coaxial cable, anyone? It will be black in color. Okay. When you remove that cover, you will find metallic mesh, and within the metallic mesh, you will find white color dielectric. Once you remove the dielectric, inside you will find a copper wire. How many of you have seen this? Whatever you say, we were much more curious than you. When the cable guy came home, we would go stand next to him, see what he is doing, and we used to learn things. That is before my PhD. Okay, in my PhD days, these things are not every day we used to see in the lab. You people don't seem to have even that curiosity. Okay, so now the space between the conductors of a coaxial cable have A equal to 0.15 mm. See the size. Every problem is trying to teach you something. You have to keep your eyes and brain open to understand what it is. A is 0.15 mm and the outer radius is 2.1 mm, very small. Find the capacitance per unit length. So capacitance per unit length is 2 pi epsilon naught divided by natural log of B by A. Substitute. Natural log. See, both are millimeters, so I don't have to do any conversion here. I can simply put them as 2.1 divided by 0.15. Take out your calculator. Please remember there are two logarithmics. LOG is log base 10 and LN is log exponential log. The other one is log base 10. Not this, we want this. Okay. So use this and then finish the problem. You will get 21 picofarad per meter. 21 picofarad per meter. Please remember when decent authors write a book, they always write numbers which are realistic. If you see some book written by some Ravi Sharma or some other fellow sitting in India, when he writes a book, you take a physics book, you see, he will write a capacitor with capacitance 2 farad. has a radius 1 meter. Okay, but then when a person who knows the subject writes it, this is the way they will write. That's the reason why this book is so famous and it continues to be famous. Okay, now that we're done with it, let us start off with capacitors in series and hey, time is up. I'm sorry. I'll stop here. Any doubts?
No.
Have you followed what I've been doing in the class today?
Yes,
Yes,
ma'am.
ma'am.
Okay, great. Fine. Let me just stop sharing. Let me stop recording. And please, about the lab, we will let you know for the next week, okay? Don't just say, Madam told it is not there. Now that the exams are postponed, we may be having our lab.